So we're going to start off with Cartesian geometry. Cartesian, of course, named after everyone's favourite mathematician and philosopher, René Descartes. I think, therefore I am. Distance formula, basically Pythagoras when you think about it. There it is, in all its glory. Something we've seen many times before, I'm sure. And quick little example, we've got to find the distance between -1,3 and 3,5. So we sub it in. By the way, a couple of things here to point out. I think sometimes people get paranoid. They say, oh, well, look, if that's x2, then you must use that y value for y2. No, you don't. Because if you get them the wrong way around, it's not a big deal because you're going to square them anyway. So you're going to get the same answer. Just make sure the x value is with the x value and the y value is with the y value. That's the main thing. And what do we end up with this one? 2√5. So basically all you're doing is finding the length of the hypotenuse of a right angled triangle. Now midpoint, as the name suggests, is the point that's in the middle of other 2 points. Well, how do you find the middle of something? You average. So that's all we're doing here. We average the x values, we average the y values. Again, it doesn't matter which way around because you're adding them. So as long as you got the x's with the x's and the y's with the y's, you're okay. So if we did this one, there we go, what do we end up with? A half 5/2. So there's two very common formulas that will come in useful with different coordinate geometry problems. Now why do I now want to talk about Euclidean geometry, named after another wonderful mathematician, Euclid? Because the interaction between them is great. They're both geometry. So you can use Euclidean geometry to solve Cartesian geometry problems and vice versa. So all the ideas that you know from Euclidean geometry, angle sum of a triangle, all those sorts of things can be used in Cartesian geometry problems. So for that reason, let's look at the quadrilaterals in particular. So how do you classify them? Well, you classify them depending on the features that they have. It's like a little family tree and you branch down to get more specialised as you go down. So you start off with the most basic quadrilateral, that is the quadrilateral, and then you can branch down and get all the other ones. Now, whatever it branches from has those features. So, for example, I think the example I used there was a rhombus. Yeah. So a rhombus will have all the features of a kite, a parallelogram, a trapezium, well, a quadrilateral for that matter, and it may even have some of its own as well. So all right, we start with a quadrilateral. If that's all we know about the shape, what could we say about the shape? It's got 4 sides. It's pretty useful. It's got 4 angles. Fantastic. That's pretty much it. So other than that, I mean, what can we tell? Not much else because we don't know anything else about the shape. So then we start branching off. What about the kite? What makes a quadrilateral a kite? And I guess the key things are, we know that you have a pair of adjacent sides are equal and you get that kite shape. So the adjacent sides must be the same. The other thing though, you don't need that information to know it's a kite. The diagonals in a kite are perpendicular. So that could be a feature that you know. And of course there's the area formula. Yes, that's the area formula for a kite. A lot of people think it's the area formula for a rhombus, but it's not. It's the area formula for a kite. It's just the fact that the rhombus branches off kite, so we can use that formula to find the area of a rhombus. Okay, let's go to the other side. A trapezium. What do we know about a trapezium? Well, it has one pair of parallel sides. We know that. And if we know it's a trapezium, then we've got an area formula that we could use. A half height, A plus B. So the perpendicular height, the sum of the 2 parallel sides. Okay, but then we branch down to the parallelogram. Our trapezium becomes a little bit more refined. Now it's not that one pair of sides are parallel. In fact, you've got 2 pairs of parallel sides now. What do we know? Okay, once we know it's a parallelogram, well, we know opposite sides in the parallelogram are going to be the same length. We know that. We know the opposite angles in the parallelogram are the same size. We also know that the diagonals in a parallelogram bisect. And if we know it's a parallelogram, we can refine our trapezium formula a little bit more and simply say, oh, well, it's the base times the perpendicular height. Now, why can we do that? Well, because if you look at the trapezium formula, remember the sum of the parallel sides? But we're now saying parallel sides are equal. So instead of A plus B, if you like, we're going to have B plus B, which is 2B, cancels with the half, and we get BH. So that's how we refine the formula down to be the formula for a parallelogram. Oh, but by the way, if you want to show it's a parallelogram, yes, you could show any of those features, but also this one here, it's good enough if you just look at one pair of sides and you know they're both equal and parallel, then the shape has to be a parallelogram. There's nothing else it could be. So you don't actually need to know things about all the sides. All right, so kite, we've got our parallelogram. Parallelogram, we can refine it a bit more. We can now make it a rectangle. So what now do we know? Well, actually, those angles now we know are 90 degrees. They can't just be anything. But as soon as we know it's a 90 degrees, I've got a parallelogram with an angle of 90 degrees, I know it's a rectangle. The diagonals now become equal. And again, we can refine the formula a bit more now and simply say, oh, it's length times breadth. Well, what about our rhombus? Now, a rhombus is both a kite and a parallelogram. So it has all the features of the kite and it has all the features of a parallelogram. But what now happens is the diagonals will bisect the vertex. So that's an additional piece of information we now know if the shape's a rhombus. Then we get to the perfect quadrilateral. It's the one that is both a rhombus and a rectangle. That is, of course, the square. The square basically has no features of its own. It's just that it has all the features of all the quadrilaterals, and when you combine it all together, you get a square. But it felt like we needed something there, so there's a formula for the area of a square. S squared. Okay, so that's what we could use. So all right, let's do an example. We've been given the 4 points of this quadrilateral, and that's all we know at the moment is it's a quadrilateral. We want to show it is indeed a rhombus. So I want to be able to prove some of these features. There's different ways I could go about it. How did I go about it? The first thing I did is I found the midpoint of AC. So in other words, the middle of that diagonal. And it's 5 on 2 minus a half. Now I'm going to find the midpoint of BD, and I notice it's the same point. So I now know the diagonals in this shape bisect each other because they've got the same midpoint. Well, if that's true, I know it's a parallelogram. So I now know the shape's a parallelogram because the diagonals bisect each other. So I've refined it down, but I want to get to the rhombus. So I've got to refine it some more. Well, I found the length of CD turns out to be 5. Then I went and found the length of AD. It's also 5. So I now know that I've got a pair of adjacent sides that are equal. Hang on, I've got something that's both a kite and a parallelogram, got to be a rhombus. So basically I'm saying I've got a parallelogram, but I've got adjacent sides equal as well. So I now know I can refine it down. The shape is a rhombus. Now remember, it is a proof, like any other proof. So that's why you are explaining yourself as you go. I'm putting reasons down there. So right, this is why I can say this, and so on. Okay, well that'll start us off for the term anyway. 7A.